All right, here we go, day 3 of sequences and series. Most of what we're going to talk about today is the sum of a sequence when you start adding all the terms of it. Now, in class we talked a little bit about where this came from and a little situation with a famous mathematician. I'm just going to jump right in here. So we have several formulas for finding sums. Okay, so this first one is the sum of an arithmetic sequence. So if you figure out that you've got something that you're adding the same value over and over and over, so here for instance would be a series, and we're going to let it be finite because it has a last value, it's arithmetic, we have some common difference of d. All right, so the sum, if you were to write them out, remember this is your summation symbol, so you're going to be adding. If you're adding all these terms up, not just listing them, but adding them, you have a couple different options for figuring out what they add up to. Now remember, on your test, you don't get to just type it all in your calculator and add them up. I'm going to be looking for the algebra that supports it. So this first one, this is one formula that you can use. You have to pay attention to what it requires you to know. So you have to know how many terms there are. You have to know the first term, and you have to know what your last term is. If you know those things, you can use this formula. Another option would be this one. If you perhaps don't know the last term, which a lot of times it'll just say, hey, what's the sum of the first 50 terms? So you don't necessarily know what the last term is. Then use this formula. Take the number of terms, divide by 2, still have to know the first term, you have to know how many terms there are, and you have to know what the common difference for your sequence is. Then you can use that one. All right, let's try it. Here's a here's a sequence, and if you look at it, it looks like we are minus 4, minus 4, minus 4, and then you're going to minus 4 a whole bunch of times until you end up at negative 51. And we want to add all of these up and see what their sum is. So it is arithmetic, but both formulas require that you know how many terms there are. And since I have the dot, dot, dot going here, now I don't know how many terms there are. So to find that out, I'm going to look at this negative 51 and say, well, that's my last term. Where would that fall? So go back and use your arithmetic explicit rule that says you have to start with the first term and then you're going to add d n minus 1 times. Well, I'm going to put in this negative 51 here. So negative 51 is my nth term. My first term is 5. I am subtracting 4 n minus 1 times. So I'm going to look for this n as the nth term. So it's negative 51. N is what I'm looking for to see how many terms it would take to get to that value. So let's do a little bit of algebra. Be sure to distribute your negative 4. Don't subtract the 5 and 4. I'm getting n to equal 15. That will be important for us to use in our formulas. Now I know the number of terms. There were two things that they wanted me to find. They wanted me to write the summation notation, and they wanted me to find the sum. Let's start with the summation notation. Remember that summation notation looks like this. You start off with n equaling something. I typically make it start off at 1. I can adjust that later if I want. And I can write the rule over here just as an arithmetic rule. The first term minus 4 times n minus 1. That's the rule that defines this sequence here. Now I'm going to let n equal 1, and it's going to increment and increment and increment. I'm going to keep plugging it in until I end up at negative 51, which I found was 15 terms. So there's our summation notation. I would expect you to clean this up a little bit Go ahead and distribute your -4. We could probably make this rule look a little bit nicer. So I'm going to take my 5 minus 4n plus 4 ends up being a 9 minus 4n. So my official answer is that's my summation notation. One more problem. Let's go find the sum. I have two options for those rules. Look back at that previous slide to see what your options are going to be. And let's decide, that first rule was probably easier to use. So if I know I know the n, I know the a1, I know the last term, let's go ahead and just use that first rule. N is the number of terms. In parentheses, I put my first term plus my last term, put it all over 2. Sorry I got interrupted there, but in the end, after you did all the math on that, you should have gotten a negative 345 for the sum of all the terms. That previous example showed what to do when you were trying to find the sum of an arithmetic sequence. Let's look at what happens when it's a finite geometric sequence. Geometric sequences have their own rule. If you're adding up several terms of a geometric sequence, you can use this formula to find the sum of those without sitting there and adding it all up on your calculator. Looking at this one, we've got several things that we still need to know before we can use it. We've got to know the first term, we've got to know the common ratio, we've got to know how many terms there are. Let's try one. Looking back at the previous page, look at that formula. You need to know the first term. We've got it. It's -2. We have to know the common ratio. We could figure that out. Let's look at what we're multiplying by. To get from a -2 to a 6, or from a 6 to a -18, it appears that our common ratio would be a -3. What we don't know, however, is how many terms there are. This sets up and gets started, but with the ... I get clear out to here. I have no idea which term number that is. So let's begin by finding out how many terms there are. And this is just like the last one, only it's geometric instead of arithmetic. So let's look at what that's going to end up being. To find the nth term, now I'm using my geometric rule. Let's fill in what we know. The nth term, I'm going to figure out this nth term, so fill in all the values. Do not multiply your -2 times your -3 because of the order of operations. You're going to want to divide that 39366 number by -2. I get -19,683 to the n minus 1. And then this takes us back. Do you remember what to do when you have your exponent caught up here? When you get your variable caught up here in your exponent? We have to switch this to a logarithm. We're going to end up doing some logs in this chapter. On these geometric ones where your n value is caught up in the exponent, you might have to do a log to get it out of there. So let's remember how to set that up as a log. It's log base -3 of -19,683 equals your exponent. Now you would type this into your calculator, log, and some of you can do that in your calculator. Some of you do that change of base where you take log of the bigger number divided by log of the smaller number. Go ahead and try it and let me know what you get for your n. I'll wait. Go ahead. You type it in. What was that? Did you say you have an error? Yeah, you're going to have an error on this. We cannot have a negative base value on our log. But let's think about what's going on here. Basically you're saying negative 3 needs to be raised to a power to get a negative number. Well, as long as this exponent ends up being ends up being an odd number, it would make sense that this is going to end up negative. So don't get caught up worrying about those. It's really just 3 to some power is going to get me this 19,000. So let's find the log and let's not use the negatives. So then you're just doing log of your bigger number divided by log of 3. And don't put the negatives on it. And you can see, oh, well, that comes out beautifully. That's just going to be 9 equals n minus 1. Add the 1. We get n to equal 10. So now we know how many terms there are. There's 10 terms. This value right here is the 10th term of this big long sequence. With that knowledge, we can now use well, let's start with our summation notation, I guess. You put your rule over here as part of the summation. Your first term multiplying by negative 3 to the n minus 1. There's going to be 10 terms. There's not really a great way to simplify that like we did the last one. You can't multiply the negative 2 and the negative 3 because of order of operations. I'm just going to keep this as my final answer for this summation notation. Last part, actually find the sum. We have all the information we need to use your formula. So looking back at your previous notes, the formula for geometric sequence, for a geometric sum, take your first term. We know that it's a negative 2. Multiply it by 1 minus negative 3 to the 10th power. That's all over 1 minus negative 3. Some things I want to notate here that I see as common mistakes. This business right here, a minus minus. So many people want to immediately go plus plus on that. You can't do that because of the order of operations forcing you to do this exponent before you do that subtraction. If you do this exponent, that's going to turn that negative 3 to the 10th power. So let me type that in. Well, I'm just going to type it all in my calculator, but just remember that you cannot change those signs. You should type this in as is in your calculator. You can't add those together because there's no power. So that would end up being a 4 for a denominator. So I'm just going to type the numerator in my calculator as is with all the parentheses. I got 118,096, and if I divide that by 4, I get a sum of 29,524. That seems a little bit weird since my biggest number is bigger than that, but notice that it's alternating signs. You're going to have some positives and some negatives, and so that's going to counter it, so it's not going to get quite as big as what you might think it should. All right, let's move on. What if it's an infinite series? And we had this on our homework yesterday where I gave you a summation that had a little negative sign in it, which seemed weird, like how do you find the sum if it's infinite? Well, sometimes you can't. But look at this scenario. Right here I have a sequence, 0.6 plus 0.06 plus 0.006. Can you see the pattern of this sequence? Would this be arithmetic or would it be geometric? It appears I am dividing by 10 each time. That's what's making that decimal move backwards, which means I'm actually multiplying by 1/10. And if I were to take these values and add them up, it starts to look like this. And if I kept adding it up, I would really just keep adding 6s as it goes. And what is 0.6 repeating? Well, that's really just 2/3. And I'm really better off. The more of these, the closer I get to infinity, the more values, the closer this becomes to 2/3. because I really want this to go on forever. If we can create some sort of a scenario like this where the values get closer and closer and closer to some value, like this one gets closer and closer to 2/3, then we can say that it does have a sum. It's actually a limit, which we haven't used this notation yet. We will in the future, but it's basically saying that as n approaches infinity, there's a limit, like it's getting close to a value of 2/3. So we have options here. If you have an infinite series, it can converge, which means it will approach a limit. So this example, this converged. So it has a limit, or it has a sum. It doesn't always converge. If it doesn't approach a limit, then we say it diverges. And if that's the case, no limit exists. Let's just look at some and see if we can decide. Is it converging towards something, or is it diverging? On this first one, 1 plus 2 plus 3 plus 4, it's just getting bigger and bigger and bigger. That is not converging towards anything. We would write diverging. The next one, I have 1, -1, 1, -1, 1, -1. That is not going to converge to anything. It's just going to bounce back and forth, back and forth, back and forth. It never hits in between there. It's just one or the other, one or the other, one or the other. That's going to be a diverging situation. This last one, 4 plus 2 plus 1 plus 1/2. What is it that we are doing here? Looks like we're multiplying by 1/2, and this value would keep getting smaller. I'd have a 1/4, and then a 1/8, and a 1/16, and this little bit that I keep adding in here is going to get smaller and smaller and smaller. That's what happens on a converging problem. That one does converge. So that means that we can find the sum of that one. Now what's special about that one is that these numbers here keep getting smaller and smaller and smaller. So what type of sequence would that happen where your numbers get smaller and smaller and smaller and smaller? It would happen every time that your R value is less than 1. That's the absolute value of yours. So not negative, just a fraction. So that last one I was multiplying by 1/2. That's what made it converge, because the common ratio was less than 1. If your common ratio is some sort of a fraction, that's a clue that it's going to be converging, and then you can find the sum. Let's look at these last two examples here and see if we can decide if they are converging and diverging, and if they converge, we want to find the sum. Oh, I forgot. Hey, look, here's another formula right here. If the infinite series converges, we can find the sum, and this is our formula for that. And actually it's a pretty simple little formula if you have an infinite one, so it's much nicer than some of those other ones. Looking at this first problem here. Compare it to your geometric rule that we have here. This is your first term, got it. Taking it times something to a power, taking it times something to a power. This looks like a classic geometric explicit rule. Look at what your R value is. It's 2/3. Well, that's less than 1. So we can find the sum of this. I think it's sometimes helpful to expand the sum so that you can see what's going on. If that helps you to find the sum, go for it. Especially to find this first term. Let's plug in 1. 1 minus 1 is 0. 2/3 to the 0 would just be 1, and 1 times 4 is 4. The first term is 4. Over 1 minus my common ratio was 2/3. That will become 4 over 1/3. Bring that up and multiply by the reciprocal, and you're going to get a 12 for a sum. Now I didn't expand this summation, I just found the first term, but if you were to expand it, you'd find that they keep getting smaller and smaller, and eventually they're going to add up to something pretty close to 12. Let's look at this example here. This time, the thing that's being taken to the power is the 4. 4 is not less than 1. So this is not going to be something that converges. This diverges. And so on those problems, just write diverges. And you won't go find the sum because the formula doesn't work unless it's converging. All right, this part here I'm not going to go over. You can kind of look through that, try some things on your calculator, follow this along. There's going to be a question on your test that's bonus. If you want to go through that, there's your chance for some bonus points. And then I just gave you at the end kind of a summary of all the different formulas. On your test, I am going to give you like a formula bank, but I'm not going to tell you what anything stands for. You have to know these well enough that you could pick it out of a pool of different formulas. You need to know your recursive rules for both arithmetic and geometric. You need to know your explicit rules. We use these inside and out. I would hope that by now you know these formulas. These are your sum formulas. So if you're looking for a sum of either an arithmetic or a geometric, you can use either of these, depending on what you know. You can use this for a geometric. You can use this if it's an infinite geometric, and arithmetic sequences are always going to diverge, so we don't have a formula for that. Try to study these so that you sort of know them pretty well without peeking at them. That way on your test you can quickly figure out which one's which out of the question bank. Hope this helps. Good luck.